This is AQA GCSE Chemistry. It's a dual award topic, which means, of course, it's also within the triple award. This is part 4 of the periodic table. I'm going to recommend you pause as you go, try each activity, and then you get to see how effectively you are learning it and how you could explain what your thoughts are with confidence within an exam. So let's start off by looking at the objectives. In this video, we're going to focus on the halogens, group 7. We need to know a little bit about how they behave, and we need to be able to describe the properties of group 7 elements as we descend the group. As a first question, we're looking at the fact that halogens exist as diatomic molecules. What do we mean by that term? And if we take the word, we can break it down. Di is 2, atomic, atoms. The elements exist as pairs of atoms. We have to remember that. We're going to see that in much greater detail when we do covalent bonding in the next chapter. But as an example, fluorine exists as F2, chlorine, Cl2, bromine, Br2, and iodine, I2. And that is something that will be of huge importance when you come to balancing equations. For the next task, I am just going to do a sketch of this graph when I review it, but it might be something you want to do so you've got a good visual representation of melting points. But key here is a description of the trend in melting points as you go down the group. And what you can see is that the melting point will increase as you go down the group. Now, when we move into the bonding topic, we will discuss further why that is the case. But it's to do with the fact that there are stronger intermolecular forces because the molecules are getting bigger. And a little bit of information down here. We find that the halogens do not conduct heat and electricity. Chlorine is a pale green gas, bromine is orangey red, and iodine is a darker red-brown colour. All important facts to remember. We're going to take a look at some reactions of halogens and some synoptic information from earlier chapters as well. So have a go at these questions. And in terms of electron configurations, we looked at these in the previous chapter. Fluorine is 2,7 and chlorine is 2,8,7. Fluorine has 9 electrons, chlorine has 17. We remember the first energy level holds 2, subsequent energy levels hold 8, and we fill from the inside out. Now, what group are the elements in? They're in group 7. It's in group 7. There are 7 electrons in the outer shell. We can see 7 electrons in the outer shell here, 7 electrons in the outer shell here. If group 7 elements were to form an ion to get a full outer shell, what is the easiest way they could do it? The answer is they will gain 1 electron. And if they will gain 1 electron, that will give them a charge of -1. And again, in the atomic structure topic, and we will look at it again in the bonding topic, there is extensive information about how we can determine the charges on ions. We're going to move on. We're going to look at reactions with hydrogen. Have a read through and try these out. And again, what's really important for me is finding common links between facts to help them more manageable. So for example, we're starting with X2. X is the halogen. So let's put the F2, the Cl2 and the I2 in. And we're going to put those down. We've got them as gaseous. Actually, the iodine arguably could be a solid, but it could sublime as well. We're reacting them with hydrogen. Hydrogen, just like halogens, is diatomic. And then we make our hydrogen fluoride or hydrogen chloride or hydrogen iodide, replacing the HX in the general formula, but then we need to balance it. I've got 2 Fs, 2 Cls, 2 Is. I need 2 in front of each of these to do the same, and that's also balanced the H's as well. We're then taking a look at the bit down here. Fluorine is the most reactive. The reaction is explosive. Chlorine is explosive. Bromine won't react until 300 degrees C. And platinum will react, iodine will react at 300 degrees C, but very slowly. So that tells us the order of reactivity. Fluorine is the most reactive, then chlorine, then bromine, then iodine. This is the opposite to group 1. Reactivity decreases as you descend the group. Okay, there's a really important practical in Group 7 that you will have seen. We are going to take a look at it, and I'm going to start you off with a table that you can then think about filling in. Safety is important. It could be that you would be asked about cyclohexane being flammable, chlorine being harmful, bromine being toxic. But this table, where we react chlorine water or bromine water or iodine water against potassium chloride, potassium bromide or potassium iodide, you could be expected to fill in this table any aspect of it, and also talk about observations and changes in any of the reactions that take place. I'm going to recommend that you try to explain what each of the three reagents on the top look like, what each of the three reagents on the side look like, which of these reactions you wouldn't do, which reactions would take place, which reactions wouldn't take place, and then we can have a think about equations for the relevant ones. So if we want to break that down, if I've said quite a lot there, let's think about what we would observe just looking at a sample of KCl, KBr or Ki. In every case, they are a colourless solution. What about when we look at chlorine water, bromine water and iodine water? In this case, we'll have a pale green solution, we have a light brown or pale brown solution, and we have a darker brown solution for iodine. Now let's think about which reactions we would not do. Bear in mind these are displacement reactions. Well, there's absolutely no point trying to displace chlorine with chlorine, or bromide with bromine, or iodide with iodine. So we're not going to do those. So we only have 6 left. Now let's focus on what we think will happen if we add chlorine to potassium bromide or potassium iodide. In both of those cases, a reaction would take place. Chlorine is more reactive than bromine and iodine, so chlorine can displace bromide and can displace iodide. What would we observe? Well, we would make bromine in this case, which is a pale brown solution. We would make iodine in this case, which is a brown solution. If we move on to the next column, you can see here, bromine cannot displace chloride in potassium chloride. There will be no visible change. But bromine is more reactive than iodine, so it could displace iodide ions, giving us the brown solution. We've made iodine. We know the colour of it from here. Finally, iodine cannot displace chloride or bromide ions, so there is no reaction here. So now let's move on and have a look at which ones reacted, and let's have a think about the equations. We can see which ones reacted here: chlorine with potassium bromide, chlorine with potassium iodide, and bromine with potassium iodide. So I've put those on here. And the colour change, in each case, we see a colour change. In the other three, there would be no visible change. And we're going to talk about what the colour changes are again in a second. Let's write the equations. Chlorine plus potassium bromide goes to bromine plus potassium chloride. Chlorine has displaced the bromide in the potassium bromide. The same has happened between chlorine and potassium iodide. The same has happened between bromine and potassium iodide. We need to balance these equations. I look at the K's. In fact, I look at the Cl's. I've got 2. I've only got 1. I need to balance them. I then need to balance the BRs. I've got fully balanced equations now, and you can see the similarities across all 3 of them. What observations are we going to make here? Well, I've already spoken about it, but let's take a look again. Bromine is made, so my pale green solution goes to a pale brown solution here. In each of these 2 cases, we're making iodine. My pale green solution has gone to a brown solution. My pale brown solution has gone to a brown solution. All very important observations to recall. Finally, we're going to take a look at these questions. And this is just summarising some of the key ideas. So, which halogen can displace all other halogens from solutions of their salts? I need to explain here, we're talking about the 3 that we've done. It's chlorine. Arguably, fluorine is more reactive than chlorine. So that could displace chlorine and everything else below it as well. It's important that we remember that. Which halogen was not able to displace any other halogens? Well, with iodine, there were no reactions. And from there, we can again reinforce what the observations are. We can see what the reactivity is. And in group 7, reactivity increases as you go up the group. That takes us to the end of this video. Thank you for listening and goodbye.